Hello, everyone. Hello, we are getting started with live lesson 26 today as we wind down the summer and get ready for the school year. Just around the corner, this will be the last week of the free live lessons covering the pre-algebra topics. And if you're watching this behind the scenes video and you'd like to see what we're actually writing, so you can see the book and the work that you see up here, we set up a new location at floridamathlive.com. It's a nice, little bit of a cleaner interface, easier to interact with each other on that page. Okay, so let's go ahead and get started. So we're finishing up geometry today, and the last topics we'll be covering tomorrow and for the rest of the week is just a few lessons on statistics and probability. That's what we're going to be going over this next week. Okay, so looking at understanding volume of cylinders, cones, and spheres. All right. So the volume of a solid figure is the measure of the amount of space it occupies. For solid figures like the ones shown below, you can use formulas to find each volume. The volume formulas for these solid figures are closely related to the formula for the area of a circle. Area equals pi r squared. So the main ones we're talking about today so far is cylinder, cone, and sphere. One thing you'll notice is that unlike working with area, there's going to be, so these are all versions of something that are related to the area of a circle. And as we can see, we're talking about two dimensions when we're talking about area of a circle. It's a relation with the radius and the ratio of a radius and a circumference, pi. But see how we're squaring the r. When we're dealing with volume, there's going to be something to the second power multiplied by a height factor typically, or in the case of a sphere. So a sphere is a circle rotated in 360 degrees in every direction with the radius not just swinging around on a plane, but going around like in a globe, like a planet or a ball. And as we can see, we're dealing with something to the third power as we're talking about 3 dimensions. This is still 3 dimensions. It's just that we're dealing with a circle, and there's a dependency on the height that will determine its volume, and this 1/3 is, see how closely actually the formula for a cylinder and a cone are. The only difference actually is that 1/3, right? So if we cut a cone out of a cylinder, then what's left would be 2/3 pi r squared h, right? So these are all pretty closely related, and they're all extensions in some way of a circle. So let's carry on here. So the height of a cylinder is the perpendicular distance between 2 bases. The height of a cone is the perpendicular distance from the vertex to the base. And remember, the radius of a circle is a line segment that can be drawn from any point on a circle to the center of the circle, right? So going out to the edge here, from any point drawn to the center of that top circle, and then this height factor, this distance here, how tall that cylinder is what gives this the 3-dimensional shape, right? Okay, let us know if you have any questions. What classes, the question of the day, what class are you worried about this year? Is it algebra, geometry? What are you headed into that you're have any type of anxiety or that you're looking to get extra preparation for. If you're finishing up any classes via homeschool or summer classes, and if you get stuck on anything, even if it's not on the topics we're covering here today, go ahead and take a picture of what you're working on and post it on the page or in this video, or go to floridamathexam.com. I'm sorry, floridamathlive.com, and post your question there. Okay, so the disk shown below is a cylinder, and it's telling us the volume is 450 centimeters cubed. Notice the centimeters cubed because we are talking about a three-dimensional object, and we want to find the height of this disk. Okay, so let's see if we can work this out. So the formula for the volume of a cylinder we see up here, I'll rewrite it, would be V equals pi r squared h. And now we have to decide what is given. So we have three variables that we're trying to solve for. You may say, what about pi? Well, pi isn't a variable. That's actually a number. It's approximated at 3.14, but it's irrational, so it does go on forever. The decimals on pi never end, but it is a number. It's not a variable. So if we want to solve, so we want to find the height in this problem. So maybe I'll go ahead and underline height in orange, and that's what we're trying to find. Now we need to find in this problem two more pieces of information in order to find what height would be. And to do that, let's see if we can pull some more information out of the question. So it's actually telling us here that the volume is 450. Maybe we'll do blue volume. So it tells us the volume is 450. So we're going to plug that in there. And it labels on our example here that it doesn't say what the radius is, but it shows this line that goes from the center out to one of the edges of that circle is 10. So that's going to be our radius. So let's go ahead and start plugging these things in. So radius, I can do that. That's going to be 10 squared. It used to be r squared. Now it's 10 squared. H is unknown. That's what we're trying to solve for. Volume is given to be 450. So now, as you can see, there's only one unknown letter. Oops, forgot pi. Keep that in. Can't forget that. Now there's only one unknown letter, the H. So what we're going to try to do here is, if we're doing, what are we multiplying h by? We're multiplying h by pi 10 squared, right? This multiplication is what we did to the h, and we want to solve for h. We want to get that h all by itself, right? So what do we want to do in order to undo the multiplication that is happening on this? We need to do the opposite of multiplication, or the inverse rather, and that is going to be division. So we're going to divide this by, now a 10 squared, I'll evaluate that just real quick. So I'm going to divide both of these by pi 100, right? Because 10 squared is 100, and I have to do that to both sides here. Okay, so that's going to cancel this, so that the only thing left on the right hand side is h. Now we need to do some math, right? So I'm going to do 450 divided by And since we have where is my, it's been years since I used this calculator. I'm looking for pi. Tell you what, I'll find it later. Let's approximate it. So let's do, so I'm going to show you 100 times 3.14. And that's the approximation for pi. We hit enter. So we're going to divide 450 by 315. And the reason I use this calculator is that the screen shows up better on the camera. So you certainly don't have to invest in anything this fancy. And on the EOC, you won't be allowed to use a fancy calculator like this, right? So if we were to round this to, what did it ask us for? We'll do it to the hundredths. So that's going to be 1.43 is h. That's the height that we were looking to solve, right? And it looks like the units are in centimeters, so we could say the height is 1.43 centimeters. Okay. All right. Let's move on to the next example. So we just did our first example of solving for a cylinder, and now we're going to do some calculations on a cone. All right, so go ahead and post any questions you have. Let me know which class you're getting ready for this year, if you have any worries, if it's algebra you're going into or geometry. This summer we're finishing up the free sessions this week, and we'll continue to be getting ready for the school year and starting the actual algebra and geometry material in this next week, okay? So find the exact value for the volume of a cone shown below. Okay, so we need to find the volume of this cone. The first thing to do would be to look back and see what the formula for the volume of a cone would be. And that would indeed be, it's very similar to the cylinder. The only difference is that we're going to multiply by 1/3 the volume of a cylinder. Okay, so it's going to be 1/3 pi r squared h. That's the volume of a cone. So let's start to identify what we have here. So first find the circle. I think that's maybe the easiest part. And it gives us this 10 here. Okay, if you can't see what I'm writing here, go to floridamathlive.com and you'll be able to see a picture of what we're working on. And can we use 10 for radius? Is 10 the radius? It kind of looks like it's implying that the whole base has a width of 10, right? So that would actually imply that the radius is 5, right? That would be 5, and this would be 5. Okay, so 10, it looks like, from what they wrote here, is saying that the diameter is 10. So it's not asking for the diameter in the formula, so we needed to divide the 10 in half to find the radius. Okay, so the radius, I'll put that in now, 5 squared. The h is the distance from the center of the base to the point of the cone, and that is labeled as 30, so I can put 30 in for h. And the other two numbers here are just numbers, not variables, right? So we're trying to figure out what v is. 1/3 is a number. We're not plugging anything in for that. And pi is also a number. We're approximating it as 3.14 today. Okay. So let's see how I would put this together. So I'd first figure out what 5 squared is. So 5 times 5 is 25. Multiply that times 30. Multiply that by pi, which we're using 3.14 as an approximation. And we also have to multiply this by 1/3 or divide this number by 3. Oops, looks like we missed a times there. 750 times 3.114. There we go, that looks better. Now divide by 3. And this is telling us the volume is going to be 785. Volume equals 785. Now let's practice identifying our units here. So everything we're working with is in inches. That would have been a good idea to ensure we were working with the same units earlier, or else we'd get a completely wrong answer. So they are both in inches. So this would be in 785 inches, but not just inches, but cubic inches is the units we're using there, okay? And that is what we're working on. The answer that they gave, so they actually ended up with, so in this case, this was covered up a minute ago, but the way they did it is they left the pi on there. That would be okay. So if we multiplied or divided 785 rather by pi, we'd be back to 250. So you can do it either way, unless the question specifically asks to get into a decimal or to leave it as pi. So you could say it's 250 pi, or you could say it's 785, and both of those are the same number. All right. So now we're getting into some fun examples here. Okay, so find the approximate volume of the largest sphere that can fit inside the box shown below. Find the volume of the largest sphere. So this is asking us to do, we have to do a little bit of analysis and look at the logic of this first, okay? So the volume of a sphere is based on this formula back here. Copy that down. Four thirds pi r cubed. All right, so there's only one variable in a sphere, and that's the radius, okay? Everything else is based on a constant, 4/3 pi. So really what we need to picture is, picture the center of this sphere, and let's drop a radius from that. Okay? So picture this is a balloon, perhaps, and you're blowing up the balloon, and it needs to fit inside of this box, and maybe it's a very fragile balloon, and if it touches the edges of the box with any amount of force, it's going to pop. So what is the volume of air that would fit inside of this balloon that we're going to blow up inside of this box? So we have to look at the constraints of how big we can make this sphere. Okay, so can we blow it up to the edges of the box here, left and right? We couldn't, right? Because it's gonna, if we keep blowing it up and it gets bigger, it's going to pop as soon as it touches one of these sides. All right. So what if we were looking at it from the right side and we tried to blow it up until it fit the sides of this 18, right? To see if we could make it just fill up until it touched the back of the box and the front of the box. Well, that wouldn't work because the box is too short. So we have to look at the tightest space. So what is the smallest dimension that we're working with here? Well, that's going to be the 12, because if we were to blow up this balloon or this ball any larger than you could call it the width of the balloon. A better word for it would be diameter. Because once it gained this dimension, it's going to hit the edges and it won't be able to fill up anymore. So now we have to do a little bit more thinking. So can I put a 12 in here, and that's going to tell us the volume that it's asking for? Well, be careful, because 12 is actually the distance from way up here to way down here, right? That is 12. So in that case, what would R be? So 12 was actually the diameter of this sphere. The radius of the sphere would be half of that at 6. So the radius is going to be 6. So I'm going to plug into the only variable we have with the volume of the sphere, 6. Drop everything else down. 4/3 is just a number. Pi is just a number. And we're going to figure out what that volume is. Okay, so how do we do 6 to the 3rd power? What does that mean? So that's going to be, when you do exponents, that's the same as thinking of it as repeated multiplication, that we're going to multiply 6 by itself. 3 times, not 6 times 3, but 6 times 6 times 6, and that would be the same as 6 to the 3rd power, 216. Does it tell us to leave it as pi? Nope, tells us to use decimal. So we're going to multiply 216 times pi, 3.14. Now one more time, now we have to multiply by 4/3. If you don't have parentheses, which you won't on the EOC, you won't have a calculator with parentheses, but what you can do is times 4, and then divide that number by 3. And you get 904.32. Right? 904.32. And the units here, we're working with centimeters, but it's not linear centimeters, it's centimeters cubed. And that is how we do that example. All right, making good progress. So, how about this next example down here? So a cylinder with a radius of 4 centimeters is partly filled with water. If you dropped in a solid glass ball of marble, I suppose, into the cylinder, you raise the water level by 1 centimeter. So find the approximate volume of water displaced by the glass ball. The volume of the displaced water would equal the volume of the displaced ball. Makes sense, right? Just like you fill up your drink with water to the top, and then you put in your ice, it overflows, right? So that's why we always put in the ice first, besides getting splashed. So if you couldn't see it, there's a ball in the bottom here that we dropped into our cylinder. And how much did it displace our water? So if we go back up here, that displacement is going to be a difference of 1 centimeter. So we could do that. So 1 centimeter. All right. And let's do a different color pen for some other bits of information. Find the volume. Try to keep our colors matching. Then we have the cylinder with a radius of 4 centimeters. So I could do something like this and say radius equals 4 centimeters. It's a good habit to make sure that they aren't setting us up for a silly mistake by giving us different units. If it had given us different units, we would have to be careful of that and make them into the same units, but they're both centimeters. All right, so we need to find the volume of this marble. So we're going to have to do a few things. So we need to find how much water was in there before, okay, or what the height was. That's the unknown, right? So if it didn't tell us what the height was anywhere here, right? Nope, nothing about height. So let's make that the blue color. Now this is where it can be a little bit tricky because it didn't actually explicitly ask us what the height of the water is. It's something that we need to figure out ourselves. So what we need to do is find out the differences in height based on what we are working with, and then that will give us the volume. So let's find out how much water was in there to begin with. That might be helpful, right? Now, let's take a step back for a minute. And if we find the height of this, we could do that, and then we could find out the height plus 1. Now, the other way we could do this is, instead of thinking about what the old cylinder was, so I'll just say question mark height, is this a better strategy? Or would it be better to go straight to figuring out what this h was? Okay. So if we could find the volume of the displaced liquid, then we would be able to figure out the volume of the marble. Okay, so what we're actually looking for is we just want to find the volume of that displaced marble. And we're going to do that by looking at the change in volume that happened after we dropped in the marble. And it did in fact tell us that displacement, that's essentially our h that we're going to be working with, right? With a radius of 4. Okay, so now let's have a peek at the formula for a cylinder again. And again, we knew it was related to the area of a circle. So it's going to be the pi r squared part of an area of a circle. And then it's like extending a circle vertically. So that's why we're multiplying by the h. So let's take that down. Okay. So back to this example. Trying to find a way I'm going to move this for just a second, and I'll rewrite the picture that we were looking at. So the displaced liquid, the change, as I'll say. So if we picture this as the cylinder, right? The part that we're really concerned with was the change. So this is the part that we're really concerned with. And of course, there's liquid down here, but it was the change that we need to figure out. So if that had a height, again, of 1 centimeter, and a radius, we use green, of 4 centimeters. So now we can start to plug these into the formula, correct? So I'm going to put 4 in where the radius would go. And I will put 1 in for height. That's like the height of this tiny cylinder that was the change in the volume of the liquid. Sorry about that. I got my colors mixed up. This was we were doing the radius in green and the height in orange before. I didn't. Here, let me just restart that part. So 4 squared, we're doing our height of 1, and volume equals pi. Okay, so now all we do is solve for volume. We can find 4 squared by doing 4 times 4. Multiply that by pi, or times 3.14, like so. So we have 50.24. Okay, and again, the units were in centimeters. Okay, and that would give us the volume of the displaced liquid, right? So after we dropped that marble in the bottom here, it increased that volume by the same amount. It's the same displacement. So the volume of a marble is the same amount of displaced liquid that was pushed up. Okay, let's see. So that was this example. I'll go back here. Let me put up the solution for that for just a second. Take one quick break to see if we have any questions on that one. And we'll move on to one more example in a minute. Okay. For one more second, collect any answers, questions people have, and we'll move on to that next example in just a moment. Okay, a manufacturer makes a plastic cone puzzle. The dark gray pieces are half the volume of the cone. Find the approximate amount of plastic needed to make the dark gray puzzle pieces. Round your answer to the nearest hundredth of a cubic inch. Okay, so we have the volume of a cone, so we need the formula for that. Okay, and that was again 1/3 pi r squared for the circle, and h. Okay, we need to see how far that was stretched. And the 1/3 accounts for the part of the cone that was cut out of a cylinder, right? So that's the formula for a cylinder, and it's really 1/3 of the volume of a cylinder when we're talking about finding the volume of a cone. There's also this other formula that we're going to need to find. So the dark gray pieces are half the volume of the cone. Okay, so let's do G for what we're actually trying to find, right? So we want to find how much plastic is needed to make the dark gray pieces. So I'll do volume of G, or we'll call it gray. So the volume of the gray pieces, it's telling us, is half of the volume of the cone. Let's not worry about that just this second, because we actually need to, we can't go straight into finding the volume of the gray pieces until we find the volume of the cone. So let's do that first. Okay, so we see here it's labeling the diameter going from one edge of the circle to the other edge of the circle through the center. The fact that it's pointing over here to the left makes me believe that it's just this part that is 6, so that the radius really is 6. So let me go ahead and put that in. So 6 in for R. The H is clear. The height is 9. And those are the only two variables that we need to plug in when we're talking about the volume of a cone. These other parts are constants. They're just a number. 1/3 third and pi are both numbers. I'll go ahead and write in here, maybe 3.14. That's what we use to calculate pi. Okay, so let's go ahead and find the volume of a cone. Show you how I calculate that. 6 squared is 6 times 6. 36 times 9 times 3.14. Now times 1/3, or divided by 3. And we get 339.12. Okay. Now we're going to substitute, because it would be very easy, and if this was a multiple choice test or a test of any kind, it'd be very easy to say, okay, wow, we just did some tough, brainy work there, and we found a number. We have a letter equaling a number, so let's plug it in. But remember, it's not asking us what the volume of the cone is, it's asking us what the volume of the dark gray pieces are. And that's why I took the time to make the formula for that at the beginning, to remind us we still had some work to do. Okay, so if the volume of a cone is 339.12, so I'm going to substitute in here, and instead of writing the volume cone, I'm going to leave a space here to, of course, put in this. Okay, so the volume of the gray equals 1/2 339.12. Still have that on the calculator, so I can divide by 2. 169.56. And there we have it. So let me leave, what kind of other examples do we have here? All right. So I'm going to leave this solution up for just one moment. Check on the comments. Can leave the comments and ask questions at FloridaMathLive.com. You can also put the comments or questions you have in the comments section. Let me know what class you're most worried about for this fall. The goal of these summer lessons is to get everyone prepared for Algebra 1 and Geometry specifically is the goal. We're doing 5 more days of the free sessions, and then we'll start allowing people to reserve their place in the fall live lessons, okay? Let me know if you have any questions that come up. We'll do 1 or 2 more examples tonight and answer any questions outside of the lesson today, or more questions about it in just a moment. Okay, good. So let's work through, what example do I want to try? Let's go through these over here. Let's do a couple of these examples. So which of these following statements is true? This is the one we'll work on. I'll give you about 30 seconds to think through this one on your own. Then we'll work on that together, okay? Okay, so which of the following statements is true? If you know the radius of a cone, you can find its volume. Well, it helps, but is it enough? So here's the formula for the volume of a cone. So we would need to know not only its radius, but also the height, right? So just the radius would not be enough. How about B? To find the exact volume for a sphere, use the fraction 22 over 7 for pi. Well, let's see. What does 22 over 7 give us? 3.14, and that was the approximation we were looking for, right? So to find the volume of a sphere, there's only one variable that's needed to find the volume of a sphere, and that is r. So if we know r and we use the fraction of 22 over 7 for pi, then that would be correct, yeah? If a cone and a sphere have the same radius, the volume of the sphere must be greater. So if they have the same radius, the volume of a sphere must be greater. Now, that kind of depends because it's only talking about the radius. So it's a little bit of a trick question. It may be inclined to say, well, they both have this pi and an r and an exponent. One is multiplied by a third and the other is multiplied by 4/3. So all things being equal, if on the cone, if the radius and the height have the same measure, then it would be true that having an equal radius, the sphere would have more volume. But it was not specific on what the height of the cone was. What if the radius we were doing was 2 and the height was 1,000? This would be like a tower compared to like the radius of a ball. Okay, it'd be a very skinny tower, but it would certainly have more volume. So that one is close, but it's not necessarily true. We'd have to know what the height of the cone would be in order to know that for sure. Okay, D. So far the only correct one is B. Let's see if D gives us a true statement. A volume formula for a sphere, cone, or cylinder must include the irrational number pi. Well, you tell me that for a volume of a sphere, a cone, or a cylinder, are there any of these that do not rely on having pi in the formula? They all require it. So volume of formula for a sphere, cone, or cylinder, they must include the irrational number pi. That is correct. Let me have a look at B again. It's a little bit ambiguous the way it's asking it. To find the exact volume for a sphere, use the fraction 22 over 7 for pi. That's not false, but we would still need the radius to be able to find the volume. So I'd probably take it either way on B if you had a good explanation on the test, one way or the other. Because in the process of finding the volume, yes, it's true that you use the fraction 22 over 7 would be fine. But we would still need the radius in order to actually find the volume, if that makes sense. All right, let's move on to practice question 2 here. Give everyone a minute to try that one on their own. Okay, let's work on number 2 together. If you're just joining us, you can post your questions in the comments on this video. If you'd like to be able to see what we're writing, go to floridamathlive.com and that will show you what we're working on here to see the work. All right, so a large water fountain is composed of a hemispherical, as shown below. A hemisphere is half of a sphere. 1 cubic foot holds about 7.5 gallons. How many gallons to the nearest whole gallon are needed to fill up this bowl? Okay, so let's break this down a little bit. So they're just giving us some information that a cubic foot, all right, so you have a cube, dimensions like so. Draw this cube. Hopefully it's close to a cube. Okay, 1 cubic foot, which means it would be like 1 foot by 1 foot by 1 foot. 1 cubic foot, that volume is going to be 7.5 gallons. So if we were to do that, maybe we'll do blue. Okay, so 1 cubic foot has 7.5 gallons. And it's asking us ultimately how many gallons to the nearest whole gallon are needed to fill the bowl. So when we do the volume calculation on this hemisphere, it is not going to give us a number in gallons. It's not going to tell us the volume in gallons. It's going to tell us the volume in cubic feet. So I'd be very interested to see, actually probably one of these here, probably one of them is going to be the wrong answer. It's probably going to be a trap because it's going to be the step before doing something with this 7.5. So let's figure out what the volume of this sphere would be. Something like so. And if the entire distance is 16 feet, the radius would be 8. The volume of a sphere as we can see back here, volume of a sphere, 4/3 pi r cubed. So what would the volume of half of a sphere be? So that would be half of this. If we divided this entire line by 2, which we would need to do, right? Then the 2 is going to break up the 4 and it's going to become 2/3 pi r cubed. So let me write down the volume of a hemisphere. So that's going to be 2/3 pi r cubed. So let's go ahead and find out what the volume in cubic feet that this fountain will hold. Okay, so we're going to plug in 8. So that 8 is going to be plugged in for that R. Okay, so let's do the calculation on that one. 8 times 8 times 8, that's going to be 8 cubed times, just want to make sure, didn't want us to leave pi as a symbol. So, okay, so times 3.14 times 2 divided by 3. So the volume capacity of this, or is it a bowl? Because we're calling it a water fountain, is volume equals, and we got 170, no, I'm sorry, 1072. So it would be very tempting to say, ah, got it, that's it, A, 1072, let's circle it. But we would be wrong, because this is not gallons, this is feet cubed, right? Let's go look at back here. So we were using a measurement of feet. So this is going to be in feet cubed. Okay, so now let's look at the conversion. So how do we go from feet cubed to gallons? So if we want to end up in such and such gallons, this is where it helps to understand some dimensional analysis or canceling of units. So if we are starting with 1072 feet cubed, it looks like we need a conversion. We need to go from feet cubed, cubic feet, into gallons. And how are we going to do that? So if we go back up here a little bit, and we have 1 times 1 times 1, so 1 foot cubed equals 7.5 gallons. We can also demonstrate this as a ratio. Okay, so we could write this as 7.5 gallons over 1 foot cubed. And we could do 1 foot cubed over 7.5 gallons as well. So we could write that both ways. But the reason we would do this is that when we write this down, so multiplied by over 1 foot cubed, we want to get rid of these feet units and end up with gallon units. So the numerator here is 7.5 gallons. Those are those units. So when we multiply this through, the foot cubed units are going to go away. So when we multiply this number by this number in that unit, we're going to end up with the number and the units that we are looking for. So let's do that. 1072 times 7.5. So the number is 8040. And the reason we didn't get the same number is because we rounded off. Let's do the 1071.787. Okay, so we just did a rounding error. We rounded off too early. So if we do the 1071.787, I think that's precise enough, times the 7.5. That looks better. And we get, now we rounded to the nearest scale, and it's 8038. So that was a good one. These are some good questions that make you think. 8038. 8,038 gallons. Okay. All right, I'll check one more time for questions here. Last chance, put any questions down. Thank you very much for joining me tonight. See me tomorrow, doing another live lesson at 7 o'clock tomorrow. You can visit Florida Math Live to get the nice interface here where you can actually see what we're writing, okay? And you can ask your questions on that page. We're winding down our last week of the free sessions, and we'll get right into the fall content starting this next week, okay? All right, thank you everyone. Looks like we have all the questions answered, and I do appreciate you for participating. Thank you very much, everybody, and have a great evening.